What the derivative tells us about the function. Um, it is better to draw a picture. So in this section, it is a good idea to draw pictures whenever it is possible, because pictures helps us to understand what is happening geometrically. Now, imagine a graph of a function. So at a point over here, tangent line will look like this, and slope of the tangent line is positive. Slope of the tangent line is positive. So I'll write it as, and at a point over here, at the very peak point, the tangent line is horizontal, therefore its slope of the tangent line is 0. And after that, the function begins to decrease, and at a point over here, the tangent line would look like this, and for that line, slope is negative. Less than 0. Again, at this very bottom point, slope of the tangent line is 0. Then it starts to increase. The function increases and slope of the tangent line becomes positive. So sign of the derivative tells us about the increasing or decreasing nature of the function. Here function is increasing, then when the derivative is negative, it is decreasing. Then it is again increasing. So when you have something like this, increasing 0, then decreasing, that is called a local maximum. And over here, what you have is a local minimum. Maybe I'll use a different color. Local minimum. Yeah, so in this way, derivatives helps us to understand these type of turning points and increasing regions, decreasing regions. So now let's keep this idea in a side and come back to this idea later. This will be very helpful for us. So because this gives us a direct relationship between the function, behavior of the function, and its derivative. Um, so for now, let's keep this aside and see what can go wrong. Sometimes the derivative does not exist. Remember, we talked about limits and continuity. In that discussion, we saw sometimes the two-sided limit does not exist. Left limit and right limit are different, or the function is not defined at that point. So in that discussion, we saw sometimes things can go wrong. Function may not be continuous. So likewise for derivatives, sometimes things can go wrong. Derivative may not exist for some functions at some points. So let's see some examples. A function is differentiable at x equals c only if the limit of the difference portion at x equals c exists. So here we see three examples. Look at the graph of absolute value of x. So it is a piecewise linear graph. If you pick a point for some positive x value, let's say 1.5, the corresponding graph, corresponding region of the graph, this part is a line. Because of a line, because it is a line, tangent line would coincide with this line. So for that region, tangent lines exist. That's okay. So that means function is differentiable. Next, if you pick a negative x value, for the same reason, the derivative exists. Function is differentiable. We can talk about slope of tangent lines. But something really bad happens at the origin. Take the origin x equals 0. If you move slightly to your right hand side, so from that direction, all the tangent lines have the same slope. So this line, the line on the first quadrant corresponds to y equal x. So slope of the tangent line at any point in the first quadrant is 1. So derivative is 1 for this part, this line. For the other line, derivative slope is -1. So as we approach to 0 from two different directions, you get two different answers. This is a corner point. So that is why we can see these two different behaviors, these two different limits. So this is a bad point. At this point, function does not have a derivative. We say function is not differentiable at x equals 0. So when you see a corner point like this, that's something very bad. At that point, you may not have a derivative. So to see this, what you can do is you can write down the limit definition. Limit the definition of the derivative as a limit. Now the point is how you approach to 0. You have two different directions to approach to 0. So that means we have to consider one-sided limits. This is not, we don't need to go through this whole computation, but the point is as you go to 0 from the negative side, you get -1. And as you go to 0 from the right hand side, you get +1. So the left and right limits are different, so the derivative does not exist. Hmm? So keep in mind that the corner points are bad points from the point of view of derivatives. Next, vertical tangent lines. Uh, so look at this graph. This is the graph of cubic root of x. We know the graph of y equal x cube. Cubic root of x is the inverse of x cube. So you take the graph of x cube, take the mirror image of that graph through the line y equal x. What you get is y equal x to the power 1/3 cubic root of x. So at this point, for this graph, at the origin, the tangent line is vertical. Vertical means it has no meaningful slope. So even though we have a tangent line, nice tangent line, its slope is undefined at that point. How can we see it? Think about y equal x to 1/3 dy over dx using the power rule. That's 1/3 x to the 1/3 minus 1. We talked about this definition yesterday. That is 1/3 x to the power negative 1/3. So I can write it as the cubic root of x squared. This term over here is well defined as a function everywhere except 0. So this formula is not valid for x equals 0. And you can see it from the graph as well. So origin or x equals 0 is not a good point for the derivative. At 0, this formula is no longer valid, but for every other point, it is okay. So vertical tangent lines. Corner points are bad for derivatives and vertical tangent lines. Corner points, vertical tangent lines, points of discontinuity. At points of discontinuity, we cannot really talk about derivatives because there is no way that we can draw a tangent line. So we need to forget about the discontinuities as well. Here is a theorem. I'm not going to justify the statement, but it says if a function is differentiable, then it must be continuous at that point. So if it is differentiable, that means if you can draw a tangent line at that point, then it must be continuous. There's no way that discontinuous functions have tangent lines at a point of discontinuity. So, for example, for this line, we have the tangent line exists everywhere except at x equals 2. X equals 2 is a whole discontinuity, therefore we can draw tangent lines. Then for this middle graph, everything seems nice except at x equals 0. Then again, for the rightmost graph, you can see a point of discontinuity. So when we talk about derivatives, we need to forget that one. So we need to make sure that when we talk about derivatives, we are not considering these kind of bad points, not, yeah, not differentiable points. Um, and except these kind of non-differentiable points, the functions are usually really good. Uh, let's think about some functions, like some example. Let's say absolute value of x divided by x. Since we are dividing by x, we need to make sure x is non-zero. The absolute value function, absolute value measures the distance between x and 0. Distance between x and 0. By our definition, if x is positive, absolute value is just x. If x is negative, we need to change its sign, so we multiply by a minus sign. So, for example, if x is negative 2, then minus 2 is plus 2. So now, because of that, we can write a piecewise definition. If x is positive, absolute value of x is just x. So for positive x values, replace this absolute value of x by just x. Then x divided by x is 1. Right way you can. And we need to make, we cannot take 0. If x is negative, then absolute value of x is negative x. Then negative x divided by x is negative 1. So the graph of this function, absolute value of x divided by x, looks like, for positive values, positive x values, function is always 1. That means it is a constant. So for positive x values, it is always 1. For negative x values, it is negative 1. Now, you can ask for the derivative of this function. For positive x values, derivative is 0 because this is a constant. Slope of the tangent line, slope of any tangent line is 0. The same is true for negative y values. Derivative is 0 everywhere except at x equals 0, because so derivative is everywhere 0 except at x equals 0, because x equals 0 is not a differentiable point for this function. There is a discontinuity, jump discontinuity. As you go to 0 from the right hand side, limit of the function is +1. As you go to 0 from the left hand side, limit of the function is -1. So these two are different. Because of that, it has no two-sided limit. So the function is not continuous at 0. Do you have any questions? Right. If not, let's move to um, another topic called techniques of differentiation. Um, so, last yesterday we talked about derivatives, especially the uh, definition of the derivative. We differentiated a lot of functions by hand, and in the meantime we observed some patterns like the power rule and adding a constant at the end does not change the derivative, things like that. But still we don't have uh, an easy way of differentiation functions. Always we have to use this limit definition so far. Now imagine a complicated polynomial, something like imagine something like x to the power 4 minus 3x to the third power plus 5x squared minus 7x plus 6, something like this. We know the derivative of all these singletons. Derivative of x to the fourth power is 4x to the third. And likewise, we can differentiate all these terms separately. But to differentiate the whole function, still we need to use the limit definition. Since this function is a little bit long, the differentiation via this limit definition will take a lot of time. Lot of time and lot of careful computation. So can we avoid that? Since we know the derivative of these parts, all these terms, can we combine them in some way and compute the derivative? Likewise, you can ask, what are the easy ways of differentiation functions? Can we come up with some simple algorithms instead of going through the limit? We know everything about limits. We know techniques of computing limits. So that's not a problem. The problem is it is time consuming. So to overcome this difficulty, we develop some techniques for differentiation. So here is something we already know. This is called the constant rule. For a constant function, slope of the tangent line is 0, therefore derivative is always 0. Even you can obtain this result using the limit definition. So in the limit definition, derivative f prime x equals h goes to 0, f of x plus h minus f of x divided by h. And in the numerator, both terms are the same constant k, because if a function is constant, its value does not depend on x. For every x value you have, f of x is the same. Here, that constant is k. So k minus k is 0. So even before you take the limit, you get 0. So derivative of any constant function is 0. Then we have the power rule. In this slide, I have an explanation for this power rule, but let's keep it aside. You don't need that. Uh, you don't need to know the reason for this rule. Just uh, memorizing this rule is enough for your level. If you know the reason, that's much better. But I don't think it is helpful. So let me skip that part. But keep in mind that this rule is one of the main important results we need. So derivative of x to the power n is nx to the n minus 1. And in addition to that, we have these rules. First rule is for the constant multiple. If you have a function multiplied by a constant, like 2x or 3x squared, a function multiplied by some constant. For the differentiation, the constant does not participate in computation. It stays there. Keep the constant, differentiate the function you have. For example, if you have 3x squared, keep the 3 in front, differentiate x squared. The derivative of x squared is 2x. Now 3 times 2x is 6x. Like here. So 3x squared, keep the 3 and differentiate x squared. Then sum rule. If you have sum of two functions and want to find the derivative, then differentiate functions separately and add later. Right? X squared plus x. Differentiate x squared and differentiate x, add the results. The same goes with differences. Derivative of a difference is difference of individual derivatives. X to the fourth power minus x squared, for example. Derivative of x to the fourth power is 4x to the third minus derivative of x squared is 2x. Then you can combine all these three rules, constant multiple rule, sum rule, difference rule, and write them as a single rule. This is called the linearity rule. Linearity rule is like a combined sum rule and constant multiple rule. Let's differentiate a few functions. Using these rules. First example, f of x negative 2x to the fifth power plus 6x to the third minus 2. Let's differentiate. First of all, we need to realize that this is a sum of 3 terms. Sum of 3 terms. So we can apply the sum rule 2 times. First for the first plus sign, then here for adding minus 2. So we can apply the sum rule 2 times. So it's enough to differentiate these terms separately. So now let's focus on the first term. It is x to the fifth power times negative 2. So we have a function multiplied by a constant. So that means the constant multiple rule applies to this term. Let's keep -2 in front and differentiate x to the fifth power using the power rule. So 5x to the fourth power plus, now we are done with this first term, then differentiate 6x to the third. Again, 6 is a constant, keep it in front, differentiate x to the third power. 3x squared by the power. Then we are done with the second term as well. Then, if you want, you can say minus derivative of 2. 2 is a constant. Derivative of a constant is 0. So that takes care of this last term. Now you can simplify this little bit. Negative 10x to the fourth power plus 18 x squared. If you want, you can simplify this little bit more because 2x squared is common. So minus 5x squared plus 9. That is the derivative. The simplification is not necessary, but sometimes it helps us. When things are in the more simplified form, we can see things clearly. Let me give you an example, an exercise. Can you differentiate this function? I can give you 2-3 minutes to think about this function. Think about this. Thank you, Sean. It is almost correct, but think about it. It is not 10x. There must be some little bit more. It's not just 10x. Mm-hmm. അത് ഓ അതാണ് അതെ അത് പിന്നെ I have received uh, lots of answers, but still something is missing in every answer. So let's think about this. Um, to see things clearly, let me rewrite the function because a lot of people are having trouble with this x over here. Hmm? So 5x squared, that's good for us. We know how to work with that. Then 3 divided by 2, that's the coefficient or the constant in front. Then 1 over x is, you can think of as x to the power -1. Very good. Now again, separate terms. So we have two terms, and let's start differentiating them. For the first term, 5 is a constant, so let's keep it in front. Then differentiate the function x squared. That's 2x. Nice. Then for the second term, constant is minus 3 divided by 2. Okay, let's keep it in front and differentiate x to the negative 1. So the power rules applies here. The power rule says derivative of x to the power n means bring the exponent to front, subtract 1 from the exponent. This is how it works for any power n. So let's take this power, negative 1, bring it to front, subtract 1 from the existing power. It's negative 1 minus 1 is negative 2. Now we can simplify this little bit. 5 times 2 is 10x minus 2 divided by 3, and we also have another minus sign. So both of them together makes a plus sign. 3 divided by 2. Then already uh, we already worked with this minus 1, so it is now not in the game anymore. We combine it with minus 2 times minus 3 divided by 2. So then both of them together got made us 3 divided by 2. So now this is gone. X to the power negative 2. The best way to write it is 1 over x squared. So if you prefer, you can write this whole thing as 3 divided by 2x squared. This is the derivative. Some people got this sign wrong. Some people got minus for this plus sign, and instead of this plus the negative 2, some people got plus 2. So you have to have everything correct. If you got a minus sign, that means the answer is completely wrong. Or if you got plus 2 instead of minus 2, that means again the answer is completely wrong. To have the correct answer, you have everything should be in place. But most of you got very close to this. And actually, some people got the correct answer, I can see. But what happened was many people got the wrong power. All right. Hmm. How about this? It may make it 2x. So to save our time, I'll do this. You can start working with me for this example. So let's take the first term. So let's keep minus 3 in front, differentiate x to the third power. When I do that, I bring 3 to front. So 3x squared plus, now for this term, what you can think do is you can think of it as square root 5 times square root x. That in that way it will be easier to work with this term. Because now square root 5 is a constant in front, so keep that in front, differentiate square root of x. That is x to the power 1 half. So 1 half minus 1 is negative 1 half. Then keep the constant in front, differentiate x. Derivative of x is just 1. Now the simplified version should be 9x squared plus square root 5 divided by 2 square root x minus 2. This is the derivative, not the function. Right? So now we have 3 rules. Function derivative. If the function is a constant, the derivative is 0. If the function is a linear function, derivative is slope of the line. If a function is a power function, it is another power function, but with a different exponent and constant in front. Then rules. The first rule is the sum rule, the constant multiple. When you differentiate something like this, you keep the constant in front, differentiate the function. Then to differentiate the summation, you differentiate the individual components and add them. So with these 3 derivatives and these 2 rules alone, we can differentiate a lot of other components. We would like to extend this list because you see, if we have something for summation, sum of 2 functions, can we extend this to products? Can we extend this to portions? Can we extend this to compositions? So in the next section, we'll be doing this. So let's see whether we can extend this easily to products. It turns out that this is not going to work with products. So let me write it as a count example. Count examples are examples showing you something does not work. Think about the function g of x equals x squared. The derivative is, we know, 2x. Now, if you think about x squared, it is x multiplied by x. Now, the derivative of the left-hand side is 2x. If you multiply the derivative of these 2 terms separately, derivative of x is 1, times derivative of x is 1. 2x is not 1. It is different from 1. 2x depends on x, 1 is a constant. So you cannot differentiate these components and multiply later. So do you see my point here? You cannot differentiate components separately and multiply. That means for a function like this, product like this, it is not the case that derivative of the product is product of derivatives. This is not the case. This does not work. To differentiate products, we have a separate rule. If you want to differentiate a product, you will first differentiate the first factor and keep the second factor. Don't touch the second factor. Then do this the other way. Keep the first factor and differentiate the second factor. This is the correct rule to differentiate a product. This is called the product rule. So the product rule for derivatives is a little bit different. So far we saw limit of the product is product of individual limits, things like that. We saw the rule for the summation easily goes with the rule for products, but this is not the case when it comes to derivatives. Derivatives have a different way of handling products. For example, let me say f of x is x squared and g of x is x to the third. Then f of x times g of x. It multiply these two guys and we get x to the fifth. Then derivative of the product. Derivative of x to the fifth power is 5x to the fourth power. Now let's differentiate f and g separately. Derivative of x, f is 2x. Derivative of g is 3x squared. We already know we cannot take the product of derivatives. Product of derivatives is just 6x to the third. That is not what we want here. But if you compute the right hand side of the product of f prime g plus f g prime. F prime is 2x, then g is x to the third, f is x squared, g prime is 3x. So you get 2x to the fourth power plus 3x to the fourth power. So altogether we get 5x to the fourth power. And it is clearly coincides with the product of derivative of the product. These two answers are okay, but this is not. So to differentiate a function, you need to use the product rule. You must use this rule. So with that, we can again increase the list of functions that we can differentiate. Example. Um, think of these two factors. Now, to differentiate this, first of all, let's take the first factor. Remember, differentiate the first factor while keeping the second factor constant. So differentiate the first factor. Derivative of this term is just 4x. Now you should immediately see why it is the case. And keep the second factor as it is. Then add, do it the other way. Keep the second factor, keep the first factor, and differentiate the second factor. Hmm. Can you differentiate this function? I can give you 2-3 minutes for this. Okay, thank you, Manshani. Hi. I prefer if you can rename yourselves using your registration number. That way I can easily take your attendance. Katsarani, can you rename yourself? And also Udesh Roshan. All right, lot of people are submitting answers, and I think I can show you my answer. Right. Okay, think of these two factors. The way I memorize this formula is uv prime is u prime v plus uv prime. Hmm? Because sometimes f and g usually use many times intervals. So even in the problem statement, you see a lot of f's and g's. So probably better to use some other variables, some other symbols. So think of this as u and v. It's differentiate the first term, derivative of x plus 1. It is a line with slope 1, so its derivative is 1. So 1 times 2x squared minus 3x plus, now let's keep the first factor and differentiate the second factor. Derivative of 2x squared is 4x minus derivative of 3x is 3. If you want, you can simplify. Thank you all for your answers. So 2x squared minus 3x plus 4x squared minus 3x plus 4x minus 3. The simplification step is not necessary, but sometimes it helps us. So anyway, I'll do it for now, but I may not do it again. 6x squared uh, minus 2x minus 3. This is the derivative. Mhm. They mean to ask the derivative of x plus 1. Should it be 2? No. Derivative of x plus 1. Uh, you can use the sum rule. Derivative of x is 1. Derivative of 1 is 0 because 1 is a constant. Derivative of a constant is always 0. That's one way to think about it. Apply the sum rule. The other way to think about it is x plus 1 represents a line. Um, Along a line, derivative is always constant because slope of the tangent line coincides with the line. So slope of the tangent line is again 1. Udesh, I prefer if you can rename yourself. Using your registration number. Now let's move to the node. We talked about the constant rule, power rule, constant multiple rule, sum rule. Then finally we talked about the product rule. Product rule. So with the product rule, we can differentiate many other functions now. And let's see whether we can differentiate quotients, ratios. To differentiate ratios, we have another rule. This is called the quotient rule. Like the product rule, derivative of a quotient is not quotient of individual derivatives. It has another little bit complicated form. So if you want to differentiate something like f of x divided by g of x, this is how you should do it. Take g, keep it, differentiate the numerator, minus, now do it in the other way. Everything divided by g of x squared. If you want to use the UV symbols, this is V U minus, so let me read it. V U prime minus U V prime divided by V squared. This is a little bit complicated, but not that difficult to memorize. Because we'll need these rules all the time from the rest of this class. Product rule, quotient rule, those are very useful. So you need to practice those. There are a lot of examples given in my notes. So please go through them after the class today. Um, let's say you have 2x plus 3 divided by x squared plus 1. So this is the numerator, this is the denominator. So to differentiate this function, we need to apply the quotient rule. Take the denominator. Now take the numerator and differentiate it. Derivative of 2x plus 3 is 2. Then the sign between them is minus. Now next do it in the other way. Keep 2x plus 3 and differentiate x squared plus 1. Derivative of x squared plus 1 is 2x. That's the parabola x squared move up by a single unit. Then take the denominator and square it. Yeah, that is it. This is the derivative of x squared. I'm sorry, 2x plus 3 divided by x square plus 1. Now I will show you some other examples in my notes. Can you differentiate this function? 3x minus 1 divided by x to the fourth power plus 2. I can give you 2-3 minutes because you need to understand this by yourself. Right. Right. 3x minus 1 divided by x to the fourth power plus 2. All right, lot of people the correct answer. So think about this as u v, then what we have is u divided by v. Its derivative is v u prime minus u v prime divided by v square. So let's differentiate. Take the denominator. Differentiate the other part minus. Now do it in the other order. Take the numerator, differentiate the denominator. Divide by denominator square. Yeah, this is the answer. If you want, you can simplify this. keep the denominator as it is, x square plus 1 to x to the fourth power plus 2 whole thing square. It is simple enough. If you expand it, you will add more terms and things will be more complicated. As a square, it is good now, and keep it, the denominator in the same way. If you want, you can simplify the numerator a little bit. But this is good enough, I think. You see, a lot of other examples are in the notes. So please go through these notes once again. And in the example, yeah, so let me show you what they have in the example. In the notes, I have expanded both numerator and denominator. This is correct. This is perfectly okay. But what I said is, if you keep the denominator as a square, as x to the fourth power plus 2 square, it looks even simpler. But these are both answers are correct. None of them are wrong. Both are correct, but it's more like a preference. Sometimes you see things like functions like this. You have a product in the numerator, and at the same time, it is a quotient. So in this case, you have to be very careful and apply the both rules at the same time. So to differentiate something like this, take the denominator, put it here, then differentiate the numerator. In the numerator, you have a product, and for that, you need to use the product rule. So take this factor and differentiate the other factor. Its derivative is 1. Then take the second factor, differentiate x plus 1. Now we are done with the derivative of the numerator. Minus, now take the numerator, put it there, differentiate the denominator, it's 1. Finally divide the whole thing by x plus 3 square. So this is just an example to show you things can be very complicated. You can have products in the numerator or products in the denominator, or maybe both. But when you carefully apply these rules, you can differentiate pretty much any function. Oh yeah, somebody pointed out a typo in fourth example. Thank you, really. There should be a correction. In the denominator, it is not x to the 16th power, it should be x to the 8, x to the second power. Sorry, 8th power. X to the 4 raised to the second power is x to 8. Yeah, thank you for that. Yeah, I should correct it. It should be x to the power 8. Then let's talk about higher derivatives. This is another thing. Think about a function, a simple one. Maybe let's take a polynomial. Hmm? Let me call it p of x. P for polynomial. X to the fifth power plus 3x to the fourth minus 2x to the third plus 5 or something like that. You can differentiate this function once again. One time 5x to the fourth plus 12x to the third minus 6x squared. And somebody can take this new polynomial and differentiate it once again. That'll be 20x to the third plus 36x squared minus 12x. You can keep doing this. You can take this uh, latest polynomial and differentiate it. 60x squared plus 72x minus 12. You can keep differentiating the function. This is the derivative of p, and the next one is called the second derivative, and the last one is called the third derivative, and you can keep differentiating f uh, as many times you want. Those are called higher derivatives. The derivatives after the first derivative called higher derivatives. Second, third. So we use this notation. You can see the notations for higher derivatives, especially the Leibniz notation. Dy over dx notation is a little bit different. Mm, And we'll see some applications of higher derivatives too. So, for example, for this given polynomial, we can see the first few derivatives, first few higher derivatives. Uh, so, keeping keep differentiating function gives you higher derivatives. That is the idea. I don't think I need to spend time on differentiating simple polynomials and power functions now. At this point, you should be able to differentiate all the polynomials, all the rational functions, and products. Our next topic is a little bit different, and it takes some time. It is about differentiating trigonometric functions, exponentials and functions, and logarithmic functions. Um, hmm. Since I have 20 more minutes, I will start talking about these functions, but I don't want to start it from trigonometry because I kept the trigonometric functions in a side in a discussion on preliminary part. I discussed about exponential and logarithmic functions. So I'll start from exponential functions. Hmm. Uh, I remind you some facts from this class. The graph of the exponential function. Typically, the exponential function usually looks like y equal b to the power x. Here b either be between 0 and 1 or be bigger than 1. For b bigger than 1, the graph typically looks like this. When x equals 0, y is always 1. So this is another b between 0 and 1 is a separate case. This is the graph for b bigger than 1. And x-axis is a horizontal asymptote, and domain of the function is set of all real numbers. Codomain is set of positive real numbers. Those kind of things we know. And near the end, so here at first we have a freedom to choose b, but near the end, I think I introduce you e to the power x. I said e is some number between 2 and 3. 2.71 something something. The property of the e to the power x is if you draw the tangent line to the graph at x equals 0, slope of the tangent line is 1. So this is how we choose our e. For different bases, we get different slopes at the origin. All of these functions goes through the origin, goes through this special point 0, 1, but at that point, different b values gives you different slopes. We choose this particular b value. That value is not at first it doesn't seem very interesting, but it has this very interesting geometry property. When you slope of the tangent line at 0 equals 1. So you may not think of this as something interesting, but it is very interesting. For example, it helps us to compute the derivative. Think about this point. That point is 0, 1. To compute the slope of the tangent line at that point, you will take a nearby point. So we set x to be h, then y coordinate is e to the power h. Then slope of the secant line is y coordinate difference divided by x coordinate difference. Then this is slope of the secant line. Slope of the tangent line is limit. The property of E is this limit is 1. For different base values, for example, if you instead of e to the h, if you take 2 to the power h, the answer will not be 1, it will be different. So E is the special number with this limit property. This is really helpful. Why? Because this gives us a way to differentiate exponential functions. So take the exponential function. Let's differentiate this function. The way we differentiate this function, differentiate means draw the tangent line at any point. This limit, the limit that we compute, it is specific to origin. It is specific to origin, but there are other tangent lines. So the way to compute derivative in general is h goes to 0, f of x plus h minus f of x divided by h. F of x plus h minus f of x divided by h. H goes to 0. E to the x plus h. You can think of it as e to the x times e to the power h minus e to the power x divided by h. See, here we have e to the power x, e to the power x. It's common for both terms, so you can factor it. And you see, the term is e to the power x. It has nothing to do with h. So when you take the limit with respect to h, e to the x is like a constant because it has no interaction with h. So you can all the way factor it to the outside of the limit. What you get is something familiar. E to the power h minus 1 divided by h. This is the slope of the tangent line at this special point. And we choose E so that this limit is 1. For other base values, this will be different. But E has this very special property. For it, this limit is 1. So derivative is just e to the power x. So exponential function with base e has this very interesting property. Its derivative is itself. For e to the power x, derivative, slope of the tangent line is also e to the power x. What does that mean? If you want the slope of the tangent line at this point, you measure the y coordinate. Y coordinate is e to the power x. Its numerical value is same as slope of the tangent line at that. So that means as you move forward along the x-axis, y coordinate increases, and at the same time, slope of tangent lines increases. So tangent lines become very steep. So slope becomes very large very quickly. So function increases very quickly. So it has this really interesting property. This is the only function with this property. All the other functions, derivative of that function will be something different. For x squared is 2x. So likewise for power functions, we always reduce the exponent by 1. We'll see other functions, especially trig functions in our next class, but e to the x is very interesting. And now that we know the derivative of e to the power x, we can differentiate some other functions. For example, about e to the power x plus 2x. This is just Um, the sum rule, derivative of e to the power x is e to the power x, then derivative of 2x is just 2. Or you can say then for the first two, we must use the product rule because that is a product. So keep the first factor and differentiate the second factor. Then differentiate the first factor, keep the second factor. So now we have taken care of this first term, first product, plus 5. Derivative of 5 is 0. So you can simplify this to be x squared plus 2x plus 5 e to the power of x. Not just the sum rule and product rule, we can do it with the quotient rule. I will leave one for you. Can you differentiate this last function? Mhm. I mean, your answer is almost correct, but except that except for the derivative of x cube. Derivative of x cube is 3x squared. Hmm? And other than that, that's perfect. Thank you, really. Nora, okay, good. Okay, shall I show you? Show you my answer for this. Mhm. So think about this as u and v. U divided by v. V u prime minus u v prime divided by v square. Uh, Thank you. Uh, Now, take the denominator. Differentiate numerator. E to the power x plus derivative of e to the power x is e to the power x. Derivative of plus 2 is 0. Minus e to the power x plus 2 times derivative of x to the third power plus 2. That will just 3x squared. Divide whole thing by x to the third power plus 2 squared. This is what you should have. This is the derivative of this quotient involving e to the power x. You could have e to the power x in both numerator and denominator, but that's okay. Um, Now, you might wonder what if we differentiate another exponential function, something with a different base, like 2 to the power x or 3 to the power x. We will discuss about this in our next class. I can easily give you the answer, but I think it needs some explanation, some context. So we will wait until we go to our next section, the derivative of compositions. In that section, I will show you, I will explain you the derivative of other exponential functions. So this is all about the exponential function. Um, Next, I will talk about uh, the derivative of log function a little bit, but not in this class. Next class. Hmm? Right. That's all for today. Do you have any questions about our discussion today about derivatives? Yeah, I appreciate all your work, especially I expect you to solve problems as I discuss in those in the class. Hmm? Uh, because especially because this is not an in-person class. I don't see you, so I I think you're looking at the class, paying attention, and thinking about the things I discuss in the class. If you are not doing that, you will have a very hard time when it comes to the exam. So please work with me, ask questions, engage with me, look at the examples, try to clarify things, because you need to study things by yourself. You need to understand things by yourself. That's the only way to learn anything. All right. Have a nice day and have a nice rest of the week.